Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll go through work 3 as part of the work or your assignment for chemical bonding. So in this first question, we have the metal tungsten, symbol W. You can find it in transition metal. Transition metal is the huge horizontal block that separates the metals from group 1 and group 2, and then the group 3 to group 8 elements. So that huge block in the middle, you will find tungsten. So you have scandium, titanium, vanadium, and then chromium. So below chromium, you will have molybdenum, and below molybdenum, you have tungsten. So tungsten is commonly used to make the wire filaments in light bulbs, and that is because tungsten has a very high melting point. So you don't want your wire filament that gets very hot in the light bulb to melt easily. So this was back in the days when we were still using those light bulbs. These days LED are more common, and LED doesn't require these filaments anymore. So LED doesn't get too hot, and LED doesn't therefore it saves you a lot of energy. Okay, LED being light emitting diode kind of light these days. But the wire glows when electricity passes through it. This is the structure of a typical metal. So the structure of a typical metal is what you would describe as giant metallic structure. And when you're asked to describe the giant metallic structure, you will have the positive cations. So the positive ions, meaning cation, that are suspended in the sea of delocalized valence electrons. It should be valence electrons. So irrespective of what diagram actually give you, so make sure that you always go back to your basic first principle, that you know that it's from the valence shell, it's the valence electrons that get delocalized. So using this structure, how do we explain how tungsten as a metal conducts electricity? So the conduction of electricity by ionic compound is a slightly different explanation from the conduction of electricity by metals. Metals do not have anions because the electrostatic force attraction is between cations and also the delocalized valence electrons that come from the metal atom itself. That's why it's only one single type of atoms and not like cation, anion, different type of atoms. Therefore ionic compound is always a compound, whereas metals are always elements. Okay, so using this structure, so the giant metallic structure has a sea of delocalized valence electrons. So irrespective of whatever they show you just now, you always have a standard that you should be able to do. That is, it has a sea of delocalized valence electrons, and these are mobile, these are free to move, they are free or mobile. Actually free to move mean mobile. Okay, so free to move means they are mobile electrons, therefore can conduct electricity. So suggest two are the physical. They purposely say physical instead of chemical because tungsten is also a transition metal, as you will learn later on in transition metal topic. So physical has got nothing to do with chemical properties. So in terms of physical properties, it will have high melting and boiling point. That is typical of any metals, to be honest, that has a giant metallic structure. What you could say is also it's malleable and ductile. So this is another properties of metal. As a result of this layered structure, then the layer can slide over each other. Each layer can slide over the other layer easily upon applying force. So applying force can, such as hammering, can actually shape it into thin sheets. Okay, so this is a graph for the same question. In a light bulb, the tungsten wire may get so hot that it melts and breaks. This relates to states of matter. I think it was work 1 or 2 that you can find in that lecture tutorial video, to do with change of state. So even though it can withstand very high temperature, but sometimes it can get so hot. That's why we get the bulb like in those old style light bulbs, they do burn out. That is a result of the tungsten filaments getting too hot that it melts and breaks, because once it melts, that is from liquid to gas, and once it break, so once broken, this is irreversible. So meaning to say, even though you can go from gas back to liquid, that is condensation, but once this is broken, you cannot reverse that, unlike the change of state. So use the graph to give the boiling point. Boiling point is liquid going to gas. This is a heating curve. So you go from solid. So here will be solid. From here to here will be solid and liquid, because this is the change of state, solid going to liquid. And I say it's melting instead of freezing because my temperature continuously going up. As my temperature continuously going up means that I am supplying heat. I am supplying heat energy. And if I'm supplying heat energy, that means I'm heating. All right. So here to here, that is a liquid state. And this is the liquid and the gas state, because I'm not too sure whether it will be very clear with the grid line. Writing in the graph is never a good idea. But anyway, I've made my case that this is a heating curve, something you learn from stats of matter, something you can relate to from one topic to another. Change of state, a pure substance, So this is the boiling point, this is the melting point. So take note that pure substances would have a fixed melting and boiling point. So they have fixed melting and boiling point. If you have an impure substance, then their melting and boiling point would be over a range of temperature. It might not be a horizontal line, it might slightly go up a little bit, or well, it's over a range. That means it's not a fixed value. The boiling point is when the liquid turns to a gas. So that is 5,500. This is 5,600. It has a unit of degrees Celsius. So be careful because they have not provided a unit there. So just writing the value is a value, but boiling point is a temperature, is a physical quantity. Always look out for units. If it is not given in the question, always write them out, because well, it's part of the skill set for being a scientist. Predict, using the graph, predict the temperature when the tungsten wire breaks. Okay, so the tungsten wire may get so hot that it melts and then it breaks. May get so hot that it melts and then it breaks. I beg your pardon, I don't know why I said liquid to gas was melting. It should be solid to liquid. All right, solid to liquid is melting. All right, so I better correct that. Solid to liquid is melting. That's this stage. Liquid to gas is boiling. So before you boil, you melt first. So when the tungsten wire breaks is when it melts. So this is the end of melting. So this is already liquid. So at this stage, it might get too hot that it will break already. So this temperature is the melting point. So you do not break when it's at melting point because you are still solid. It's only at the end of the melting point. So at the end of the melting point, I suppose this is the beginning of the melt. This is the beginning. So just after the melting point, I'll guess probably 3,500. Just after the melting point, then it will break. Okay, so around 3,500 degrees Celsius. That is when it will melt and then it will break. So next question. So this is actually actually you don't do relative isotopic mass. If you change this to relative atomic mass, that would be great. This is in your atomic structure as part of the syllabus, but actually you can see the syllabus under the next topic, but together in your notes I already covered it as a fixed definition. So looking at your syllabus and your notes, so it refers to the average. So it's to do with the average mass of an element. So these are straight from the syllabus actually. if you see the syllabus, average mass of the element, average mass of the isotopes. What am I talking about? So you have different isotopes, so you average their mass. The isotopes if is of an element, and the one that a lot of students miss out on is the comparison. This is the relative standard that you have got to remember. Okay, so 1/12, or you can just say 1/12, that would be alright. 1/12 of the mass of an atom of carbon-12. So I like to write my carbon-12 in the international notation, where the nucleon or the mass number is on top instead of at the bottom, because they are not centralized like given in the periodic table. They are to the far left, they are top left. This is nucleon or the mass number, because it is carbon-12. Okay, so important idea is average mass, talking about the isotopes, taking the average mass compared to 1/12 of the mass of an atom of carbon-12. So together with metallic bonding, they can incorporate these ideas of metals and isotopes and the relative atomic mass. So it says 63.55. So you're supposed to work out the percentage abundance of each of these isotopes and show your working. So usually they give you the percentage and then they ask you to work this one out. But here they want you to work out the percentage abundance of these and these, given that there are two isotopes. So if I let the percentage abundance of copper 63 be x percent, percentage is out of hundreds, therefore the percentage of copper 65 is going to be 100 minus x percent. So now that you know the percentage in terms of this algebraic expression, therefore the average is going to be the mass number. The mass number 63 multiplied by the percentage. Okay, you add them up. 65 is the mass number multiplied by 100 minus x. Okay, so perhaps I can just use bracket. To avoid the confusion. So I use a big bracket to add them up together. And altogether I have 100%, so it's x plus 100 minus x, which of course get to 100% because I get this by taking it away from 100% to begin with. And this is equal to 63.55. So this is going to be 100%. So 100% I can move it up and then I will get 6355. This thing, 63 times x, will give me 63x. And here's the most common mistake that a lot of students cannot do, even A-level students. So 65 times 100, because these are bracket, and then plus 65 times minus x is going to give you minus 65x. So I have more 65, I have 65x, I have 63x, so it's better if I move these to the other side, and I will get 2x is equal to 6500 minus 6355. X is equal to, do the subtraction first because you don't want to key in the wrong thing in your calculator. A very common mistake is people don't really know their calculator that well. So I get 145 and that's divided by 2 and I get 72.5%. So if x is the percentage abundance of 63 copper and that is 72.5%, so the percentage of 65 copper is going to be 100 minus that, and I get 27.5. So just by looking at the value, does it make sense or not? I have 63, I have 65. My average mass, the weighted average based on the percentage abundance, is closer to 63 than 65, much closer to 63 because I have a lot more 63 than 65. So this method is alright. Okay. So going back onto bonding, so name the type of bonding within solid copper. Copper is an element. Copper is also a metal because copper can conduct electricity. Copper wires, I'm sure you have heard of it. So this is just metallic bonding. So now you need to draw, label, diagram, show bonding. So basically this is show metallic bonding. When you have to show metallic bonding, make sure that you can draw the cation. You should draw them of roughly similar sizes because you want to show them they are the same cation, and then use space as best as you can. I just draw electrons without the circles around it because electrons are freely moving. So I gotta label it. These are metal, meaning to say copper, cations, positive ions, or you can say positive ion, whichever one you like, but you should know that cation is the term we use to describe positive ions. And what are these? These are delocalized. Make sure you spell it properly and make sure that you label it that it is valence electrons. It is not all the electrons in the atom, it's only the valence electrons, meaning the outermost shell electrons, that get delocalized because they are no longer inside the outermost electron shell. In fact, they get delocalized from their outer shell. Now they become delocalized valence electrons. Okay, so the attraction between the plus and the minus charge of the electron is going to be metallic bonding. So this is metallic bonding structure of a giant metallic structure. Okay. This is the last page of this work. So there's a bunch of substances here. Iodine exists as I2. Lead-2 bromide is an ionic compound. Pb2 plus, the 2 refers to lead-2, and metal form cations. Cations are positively charged, so Br minus, you have 2 of it, so you get PbBr2. Methane is your case study, CH4. Br2, just like iodine, just like chlorine, just like fluorine, they exist as this simple molecular Br2 because they both bromine atoms will get noble gas configuration. Silicon dioxide is SiO2. The other name is called silicon 4 oxide. Is the other name for, is the formal official name is given in the syllabus for silicon dioxide. Lithium is a metal, is an element. So use the substances name in the table to answer the following question. So you got the name, not solid at room temperature and pressure, not solid. So room temperature and pressure is 25 degrees Celsius. So look for something where it's already melted. Okay, so if your 25 degrees Celsius must be above or below the melting point. It must be below the melting point. 25 degrees Celsius must be below the melting point. That means by 20 hang on, what am I talking about? Not solid. If I have temperature, if I have 25 degrees Celsius here, if my melting point is here and 25 degrees Celsius is here, then it's a solid. Then it is a solid. I want not solid. Therefore, this is wrong. I do not want it below. I want it above. Okay, I want it above for it to be not solid. So 25 degrees Celsius must be above the melting point. So meaning the melting point shouldn't be there. Okay, so the melting point you're looking for around there. So it's no longer solid. So the melting point must be below 25 degrees Celsius. Okay, the other way of thinking about it is melting point is below 25 degrees Celsius. So that is the thing, that is the one. So methane and also bromine. So both of these will not be a solid because they will have already melted. The rest have temperature, melting point above 25 degrees Celsius. So you haven't melted yet, so you are still a solid. Melting point, the temperature for melting, that's solid to liquid. Boiling point is the temperature for the change of state from liquid to gas. Now, which substance is a liquid over the largest temperature range? Between the melting point and the boiling point, you are a liquid. Okay, between melting point and boiling point. So if you have melting point, if you have boiling point, between there you are a liquid. So finding the difference between melting point and boiling point, which are the largest. So the difference between melting point and boiling point, which one is the largest? Okay, so you can calculate the difference there. I'm gonna erase this. Oops, no, I don't want to erase the other one. I will erase this because I want to calculate the difference. Okay, so difference melting point and boiling point on your calculator. 184 minus 114, I get 70. Well, of course, this is in degrees Celsius, so I don't have to write the units all over. I just need to label it once. So this is 544. Careful with minus 161 and then minus 182, so there's 21 degrees Celsius. 59 minus 7. A lot of students always make the mistake of not understanding well, the simple maths, I guess. All right, and this is on your calculator. Imagine doing it manually. You might even make more mistake. So the largest difference between melting and boiling point is this. Therefore, lithium remains a liquid over the largest temperature range. So this has to be lithium. Now, name the substances that are non-metallic. Okay, non-metallic. This is the only metal because this is the only one that with metallic structure. So non-metallic elements. Non-metallic element means the rest of them. Okay. Name the substances, so plural. So just label all of them except for lithium. Okay. So lead to bromide, methane, bromine, silicon dioxide. So I don't use silicon for oxide because I'm using the substances name in the table. Which two substances conduct electricity when molten? So first of all, the metal definitely conduct whether it is solid or whether it's molten, because you have free delocalized valence electron both in the solid state, both in the molten state to conduct electricity. But then you also have the ionic compound. Ionic compounds cannot conduct electricity in the solid state because the ions are in fixed position. They are not free to move. They are not mobile to move because they only vibrate about fixed position in the solid state. But when it's molten, then you have liquid ions. Liquid ions can slide past each other. That means they are free to move. That means you have mobile ions that can conduct electricity in the liquid state. Liquid state meaning molten. All right. Now, why methane and silicon dioxide have different melting point? Talk about structure. So methane and silicon dioxide, they both have covalent bond, but it's not just the bonding, it's also the structure that actually determine what melting point you will have, because what forces of attraction are you breaking. So methane has a simple molecular structure. So only need to break weak intermolecular forces of attraction for melting. Okay, so we're talking about melting point here, so I'll just talk about melting. But for silicon dioxide, which is SiO2, it has giant molecular structure. So it has giant molecular structure, and because you have giant molecular structure, we need to break many strong covalent bond in order for change of state from solid to liquid. Many strong covalent bond. So I'm trying to follow the standard that we usually do, which is try and be complete as possible, whether it's 2 marks or whether it's 4 marks. Okay, break many strong covalent bonds between silicon and oxygen atoms. So in the context of silicon dioxide, it's between silicon and oxygen atoms. For melting, that is for going from solid to liquid. All right, so structure and what are you breaking? Okay, so talk about breaking weak intermolecular force. Not a lot of energy is required, so low melting point. For methane, low melting point. Negative is lower, much lower than 0 degrees Celsius. Silicon dioxide much higher than 0 degrees Celsius, because giant molecular structure, or what you would say giant covalent structure, you need to break the many strong covalent bonds, and as such they require a lot more energy than breaking the weak intermolecular forces of attraction. Okay, so that's it really. That's it for these work 3 tutorials, and if you've got any questions, feel free to raise them in class or when you see me in school. or get in touch with me. And for the rest of the viewers and subscribers who are watching this on my channel, so don't forget to subscribe to the channel, click the button on the bottom right, and follow me at ptet.chemistry for all the latest updates, and browse through the other created topical playlists on my channel as well. They might be useful to you or someone you know, so do subscribe and share the channel widely with other people. Thank you for watching. See you in the next video.